Assalamualaikum warahmatullahi wabarakatuh, everybody. So now we are moved to another topic in our chapter, work and energy. So now this one is the final, I think, for this chapter, final session for this chapter, inshallah, hopefully. So now we'll go to another topic, power and efficiency. So you should be able to determine the power generated by a machine, engine or motor, and also calculate the mechanical efficiency of a machine. Okay, power is defined by its amount of work performed per unit time. So the definition of power is the just product of work and also the time. So we need to have the amount of work by using the performed by per unit time. So work dividing by time. So a machine or engine perform a certain amount of work du within a given time interval dt. So the power generated can be calculated as a P is equal to du over dt. So in terms of the vector, so since the work can be expressed as du equal to f dot dr, the power can be written as a, now we are differentiating the f dot dr dt. So f dot dr dt is equal to, this one is a velocity, so force multiplied by a velocity, so force dot v. So this power is the scalar defined as a product of force and velocity component acting in the same direction. So we have two formula for the power. Power is equal to, let's see, the force is constant, so force divided by time, or the force multiplied by velocity. So using the scalar notation, the power can be written as P is equal to PV cos theta, so where theta is the angle between the force and velocity vector. So if the velocity of the body acted on particle force is known, the power can be determined by calculating the dot product or by multiplying force and velocity component. So the unit of power in SI system is the watt W, where 1 watt is equal to 1 joule over second, or also equal to 1 Newton dot meter per second. In this FPM system, the power is usually expressed in the units of horsepower, where 1 horsepower is equal to 550 feet dot bound over second, or equivalent to 746 watt. So what's meant by efficiency? So the mechanical efficiency of a machine is the ratio of the useful power produced output power to the power supplied to the machine input power. So the mechanical efficiency is equal to power output dividing power input. If energy input and removal occurs at the same time, efficiency may also be expressed in terms of ratio of output energy to the input energy. So energy output dividing by energy input. Machine will always have frictional force. Since this frictional force dissipate energy, additional power will be required to overcome this force. So consequently, the efficiency of machine is always less than 1. So you can see here this example. So let's say this one's a car, 2000 kilogram sports car, increasing in speed uniformly from rest to 25 meters per second in 30 seconds. So initially is a velocity is a 0, so final is a 25 meters per second. So changing from 0 to 25 per second take place in 30 seconds. So the energy efficiency is equal to 0.8. So we need to find the maximum power and also the average power supplied by the engine. So first one, we need to draw the free body diagram and also kinetic diagram. Then apply the equation of motion and kinematic equation to find the force. Then determine the output power required. Finally, we can use the engine efficiency to determine the input power. Okay, so now we need to draw the free body diagram. So the object moving with the curve with the angle slope here. So the normal force is the perpendicular to top surface. The work is must direct to the earth. So the frictional force here, we can see here the normal force NC is the frictional force, and FC represent the resultant force of all four wheels. Okay, in this problem, why is the frictional force is upward going forward? The frictional force between the wheels and push the car forward. So normally the friction force, so the friction force is backward because the object is moving upward, but the friction force is going backward. But you can see the tire, so the tire is moved forward, and at the road the tire, so at this one the tire is moving upward, but the road is become backward, so become backward, and then because this the friction force must be opposite with the movement of the forces, so the tire will become, when you contact the road, tire will become backward, so the frictional force is going forward. So that's why the friction force is forward. So equal to ME, this one is a kinetic diagrams, MS multiplied by acceleration. So we're solving using this equation of motion delta total summation force in x component equal to MEX. So this one is the mass. So you can hear here is the total resultant force here. So total resultant force, we can see here the friction force is positive. Friction force is positive here. So the W, so W, because if this W in y-axis will not because W is have the angle, it's not 100% in y, so W you need to resolve into the x component. So because it be going downward, it should be negative. So this one is a mass. So mass multiplied by G. G is a gravitational constant G, 9.81. So sin 5.711. This one is the you need to resolve angle to the in x component. So equal to 2000 multiplied by EX. 2000 is a mass. E is the expression in x component. Okay, this one we cannot solve this equation because we have two unknowns. We have the FC here. We also have EX. So but using the kinematic equation, so determine EX using constant expression V equal to V naught plus E EXT. So V is final velocity 25, V naught is initial velocity 0, time is 30. So V minus V naught over T, we can get the expression in x component 8.33. So we substitute 8.33 into the first equation. So here, so finally we can determine the frictional force 3619 Newton. Okay, so when we get the 3619 Newton for the frictional force, the maximum power output of the car is calculated by multiplying the driving frictional force FC and the car final speed Vmax, so 25. So we want to get the maximum power output. So the 3619 multiplied by 25, so given by 90.47 kilowatt. So average power output, we just get average velocity. So 25 divided by 2, the force is still maintained 3619. So what we get 45.28 kilowatt. So the power supplied by the engine is obtained by using the efficiency equation. So given by the efficiency is equal to output divided by input. So input power input maximum, so the formula should be output maximum dividing by efficiency. So 90.47 kilowatt dividing by 0.8. So what we get here 113 kilowatt. Same is if we want to find the input power average, so output average power dividing by efficiency. So we get the 56.5 kilowatt. Okay, now we move to another topic, conservation of energy. In this topic, you should be able to use the concept of conservative force and determine the potential energy such as force and apply the principle of conservation of energy. So when a particle is acted upon by a system of a conservative force, the total work done, the work done by this force is conserved, and the sum of kinetic energy and potential energy remains constant. So in other words, as the particle moves, kinetic energy is converted to potential energy and vice versa. This principle is called principle of conservation of energy. In other words, in any point, in any position, in any time, the total work must be conserved, the total must be equal. So this principle work conservation energy, because energy is converted from another type energy. For example, kinetic energy chain convert to potential energy, and potential energy convert to another energy. So energy will be conserved. So finally, we have here T1 plus V1 is equal to T2 plus V2. T1 is kinetic energy, V1 is potential energy. So T1 stands kinetic energy in state 1, and also V1 potential energy in state 2, same as T2 V2. So recall that is T is equal to half mv squared. So we can see here the one example. We can see here roller coaster here, 800 kilogram roller coaster from point A going in this roller coaster released from point A. Okay, find the minimum height h of point A so that the car travel around inside loop B without leaving the track. Also find the velocity of the car C for the height h of A. So plan, we note that the kinetic energy, potential energy due to gravity are involved. Determine the velocity at B first. We need to find also the velocity at B using the equation of motion we have learned in chapter 2 in dynamics, and then apply the conservation of energy equation to find the minimum height h. Okay, the solution. Okay, first we are placing the datum at A, so this one is become 0. So h here is a negative h here. This one is a this one there should be this one is negative h, this one negative, this one is a h negative h minus 20. So TA plus BA, the total energy at A equal to total energy at B. So TA plus BA, so initially TA is a half mv square initially at rest, so velocity at A is 0, potential energy because this one height is 0, so becomes 0. So TV is a half mv square, mv velocity at B square minus because this one is going downward, so 809 point mass or mass is 800, G is 9.81, the height is h minus 20. So this equation we cannot solve because we have the two unknown here, VV and H. So we are using the equation of motion. So we need to find the velocity at B first using the equation motion at B. So we know that this one is a curved linear. This one we have the center of the curvature. So we have this so-called the kinetic diagram. So the width mg going downwards, NB is below to 0 because this one we have focused only 2D. So only force directed along normal towards the center of curvature of point. So MAN. This one is related to the equation of motion for the curved linear. The total resultant Fn is to the MAN. So the resultant force MAN. So AN given by V square over rho. So Fn is the width because the mg equivalent to the force directed to the normal. Only this force only. Okay, so 800 multiplied by G 9.81 equal to M 800 and V square over rho. So we can determine the V velocity here given by this equation of motion. So VV given by 8.578 meter per second. So we get this VV, we put into this first equation in order to get the height. So now we now using the energy conservation. So we can put this velocity of VB, so we can determine the H at 23.75. Now we find the velocity at C by using applying the energy conservation again. So you're taking about A and also C, so TA and VA, the kinetic energy at A plus potential energy at A. So we have here, and then kinetic energy at C, so we half mv square, VC square, potential energy at C, so just minus because it's downward. So mg, the height is 23.75. So finally we can determine the velocity as at point C given by 21.6 meter per second. Okay, I think that's all for this chapter. See you again in the final chapter, chapter number 11 in our syllabus, but in dynamic referring to the RC Hibner textbook in chapter number 4. See you, bye bye, thank you, see you again in next final chapter.